All right. So again, we continue a bit and we repeat the problem of limit cycles in two-component systems, and yeah, how Hopf bifurcation can arise in a two-component system. X dot y dot is equal to f and g of xy. Okay, and well, we show it in another way, that the type of crossing that we have here between two null lines, f is equal to 0 and g is equal to 0, is not compatible with the sign pattern expected for Hopf bifurcation. For such a bifurcation, we have seen that there are two possible sign patterns. One is what is called substrate depletion, and the other one is what is called activator inhibitor. Okay, so in the substrate depletion, you have two rows with the same signs in the derivative of with respect of x of f and y have the same sign, and here also the derivative with respect of g have the same sign. Here for the activator inhibitor we have opposing sign and opposing sign for the two derivatives with respect of x and y. Okay, so let's do the following. Let's start from the intersection between the null lines. This is the fixed point f, and let's move infinitesimally close along the null line f is equal to 0 to a. Okay, so in this case a, we want to calculate the difference of function f of x, f calculated in a minus f calculated in f. All right, this is 0. The function is 0 in both points. Okay, but if this is infinitesimal, x of a can be written as x of f plus an infinitesimal increment, and y the same. Okay, so we have the following expression we develop at the first order. We get partial derivative of the function f calculating at the fixed point, and the derivative with respect of x and with respect of y, multiplied each by dx, which is the increment. So this x is the x coordinate of a minus x coordinate of f. dy is the y coordinate of a minus y coordinate of f. Okay, and this has to be equal to 0. If we solve this, we find that dy dx must be equal to minus the derivative with respect of x and divided by the derivative with respect of y, both of f. Okay, at a fixed point. Okay, but because of this null line going from f to a, dy is positive and dx is also positive. So this is a curve that it says positive derivative, so it's going up here. So dy over dx is positive for this one. Therefore, this one has to be also positive. That it means that these two derivatives, this one and this one, have opposite signs. Okay, so we conclude that in this case these two derivatives have opposite signs. But if we do the same now for b, right, and we do the increment b minus y, what do we find? It's exactly the same. We do it now for g. We calculate g in x b and y b minus g of in f, xf, yf. And this difference has to be 0 because they're both 0. And we do exactly the same reasoning. We develop to the first order, and from this calculation we find that these two derivatives have same sign. Okay, so it means that if we look at our Jacobian, we concluded these two must have opposite sign, these two must have the same sign, and none of these two conditions combined are not compatible either with substrate depletion or activator inhibitor. Okay, so we conclude that in no case this type of intersection can give rise to Hopf bifurcation. It's only when these two null lines intersect each other having the same slope, either g equal to 0 has a curve and is crossing with the same slope, or the f equal to 0 is crossing with a negative slope. Okay, that gives either of the two. Okay. Okay, so now we are ready to step to three-component systems, and we are actually looking at three-component system without autocatalysis. For two-component system, we saw that a necessary condition for Hopf bifurcation is to have autocatalysis. In this case, we just work without autocatalysis, okay? And we are looking at the system of three variables, x, y, and z, coupled in the following way. X is coupled to y is coupled to z, and z back to x. So there is a loop here, and this is described therefore by the following differential equation. Note that x dot has a synthesis rate which depends on z. So the synthesis of x is influenced by z, and x degrades with some degradation rate alpha. Alpha, beta, and gamma are the three degradation rates. They are chosen to be positive, right? So positive quantity. So this is just a normal degradation, so no autocatalysis, all right? And f, g, and h are function of respectively of z, of x, and of y, okay? So now we are looking at two different cases. The case one is the case of positive feedback, all right? Positive feedback. So therefore we have a positive loop here. X is coupled to y, y to z, and z to x. We will see that doesn't change if I, for instance, if I interchange the one of these two signs, like if I put a repressor and an activator, then it's still a positive loop. Okay, in any case, let's consider this type of Jacobian, and I call it J plus. So when I calculate the Jacobian from this set of differential equation, in the diagonal I have minus alpha, minus beta, minus gamma. Okay, in the off-diagonal term here in the first row, if I look at the synthesis of x, I have no y, so derivative with respect of y here is 0, and I have some phi, and phi is the derivative of f with respect of z, okay? And c1, c2 are the derivative of g with respect of x and of h with respect to y. So this is a simplified Jacobian. We have three zeros here, and we have an off diagonal terms phi, c1, and c2. I forgot to write here, and I will do it right away, that we mean that here that phi, c1, and c2 are positive, okay? So this is a positive feedback. Phi is the derivative of f with respect of z. So it's if we have a positive feedback, if we have an activator here from z to x, this must have a positive sign. Okay, and the same for c1 and c2. So the result of the analysis of this Jacobian, which we show in the next video, is that this type of Jacobian is not compatible with Hopf bifurcation. Therefore, we have no Hopf bifurcation for this type of sign pattern, for this type of positive feedback loop. All right. The case of the negative feedback loop that we are going to discuss also is this one is x, y, and z, activator, and then repressor. And this gives rise to the same matrix along the diagonal, okay, minus alpha, minus beta, and minus gamma. Along the off diagonal, for the off diagonal terms, I will have a minus phi. Now this is phi is still a positive, this is a minus sign. Totally, this is a negative sign. This is a sign of, this is due to the repressor action of z over x, okay? But we have c1 and c2, okay? And we can show here that in this case, the Hopf bifurcation for this type of sign pattern is instead possible. So this is the proof of the case one of positive feedback. So our Jacobian is J plus. It has plus phi here, positive signs here, minus alpha, minus beta, minus gamma. All the coefficients are positive. Okay, so we want to find the eigenvalues of this matrix and show that there is no Hopf bifurcation in this case, okay? Let's do the calculation of the eigenvalues. For that, we have to solve the characteristic polynomial. We know how to do it. We have to add minus lambda in the diagonal terms and then calculate the determinant and set this to 0. So the characteristic polynomial, we call it g of lambda, and this will be given by lambda to the third, lambda squared, terms in lambda, and so on and so on. Okay, so this is a simple calculation that one can do. So you see the lambda squared term is alpha plus beta plus gamma. We call this term A, capital A. The term linear in lambda, the coefficient is alpha beta plus beta gamma plus beta gamma alpha. We call this B. And then what is left here, we call it C, capital C. This is alpha beta gamma, which is a positive term. And we have a minus phi, so not phi 1, sorry, this is phi, minus phi C1, C2 equal to 0. So you see that all these A and B are certainly positive. The C can be positive or can be negative, right? Because there are two contributions, one positive and one negative. Depends on what wins, okay, of the two. So now we split the analysis in two cases. We say, suppose that the C is positive. Okay, we make use of the following theorem, following properties. And this is called the Routh-Horowitz criterion. So for a polynomial of third degree, with coefficient, with the following properties, A is positive, C is positive, and A times B is larger than C, if these three properties hold, then it implies, and vice versa, so these two relations are equivalent, that all real parts of the roots of this polynomial are smaller than 0. If that's the case, there is no Hopf bifurcation. All right. So A in our case is larger than 0. We asked C to be larger than 0. This is our hypothesis, and it's very easy to prove. You can do the calculations. You take the alpha A times B, show that this is larger than C. It's very easy to show that. So therefore, if we consider the case C larger than 0, certainly we cannot have Hopf bifurcation, because to have Hopf bifurcation we need that a pair of complex conjugated eigenvalues get a real part equal to 0. But you know, if this is true, then we have the real part are always strictly negative. All right. Now we have to study it and look at the other case now. Suppose that now C is smaller than 0. We cannot use this relation anymore. We make the hypothesis that C is smaller than 0. So if C is smaller than 0 and we plot our characteristic polynomial as a function of lambda, positive lambda, so you see it is a cubic, it has a cubic term, and it certainly, maybe there is something more going on here, but certainly will have a positive root, okay, here, because it starts from a negative at lambda equal to 0, g of lambda, g of 0 is C. C is negative, so it must start from here, and it goes to plus infinity, so at least there is one positive root of this. Therefore we can decompose our polynomial g of lambda, so we don't know how to calculate this one, but there should be one if C is smaller than 0. Therefore we can decompose the g of lambda in the following form. So you have lambda minus lambda plus this root, and then we have a second degree polynomial, okay, where we write in general lambda squared plus d lambda plus e. Okay, now making the multiplications here, we can relate this d and e and lambda plus to our original coefficients a, b, and c, and we find very simply these three relations here between A, B, and C. And particularly the first relation gives that D, this capital D, must be equal to lambda plus A, right? Lambda plus is a positive root, all right? A is positive, it's simply alpha plus beta plus gamma, therefore this D, okay, if there is such a decomposition, this D is certainly a positive number. But this is incompatible with the Hopf bifurcation. The Hopf bifurcation requires the D to be 0, because the Hopf bifurcation point is a point where you have two pair of complex conjugate roots that are purely imaginary, and these two roots can only come from this second part, okay, but only when d is equal to 0, right? In the case d equal to 0, the roots are precisely lambda plus or minus I square root of e, all right? Or minus, well, yeah, square root of e, yeah, that's correct. Then in this case, we will have a Hopf bifurcation, though, therefore the Hopf bifurcation must happens only when d is equal to 0. But we have proven here that d can never vanish because it's the sum of lambda plus a. Therefore, again, in this case, also in the case B, when c is smaller than 0, there cannot be Hopf bifurcation. The conclusion is therefore that this case 1 of positive feedback never can show any Hopf bifurcation. Okay, we consider now the case 2, which is negative feedback. The Jacobian is J minus and differs from the previous one with for negative element here, minus phi. Phi, again, C1 and C2 are positive. All right, so again, calculation of eigenvalues, it gives a characteristic polynomial very similar to the previous one, but now I have alpha times beta times gamma plus phi C1, C2. And this is definitely a positive number, okay? Let's call this one C. As before, this is certainly positive. All right, now we have A larger than 0, C larger than 0. However, so we know that if A times B is larger than C, the case is discussed before, that then all the real part of the eigenvalues is negative, all right? But it can happen now that you see that this situation, so that A times B is smaller than C, all right? C is a positive number, and if phi is sufficiently large, okay, then A times B can become smaller than C, okay? So therefore, we break this theorem, and it's not all the real part of these eigenvalues is not necessarily smaller than 0. In particular, let's study the case when A times B is exactly equal to C. So what happens to our characteristic polynomial? It takes this form, and we can easily decompose it, right? If C is equal to A times B, I replace instead of C A times B here, and finally the composition gives lambda plus A and lambda square plus B, multiplying. Okay, so this is precisely Hopf bifurcation. You see now here we have 3 eigenvalues, right? One is minus lambda, all right? This is a stable eigendirection in our system. And then we have lambda square plus b equal to 0, which gives lambda plus or minus e square root of b. This is a pair of purely imaginary complex conjugated eigenvalue, and this is precisely the Hopf bifurcation. So this negative feedback case is exactly compatible with the Hopf bifurcation. You must have that A times B is equal to C, and this happens if this phi is sufficiently large, or phi times C1 and C2 is sufficiently large. The final remark is that here everything comes into a combination. Phi enters as a product with C1 and C2. For instance, now we have considered the case where C1 and C2, they are both positive. I can take both negative and swap the sign, minus C1, minus C2, nothing changes here. Okay, this is still a positive feedback loop, if you, a negative feedback. Also, if you have minus, minus, and minus, 3 negative terms gives rise to a negative feedback loop. So what is important here is always the product of C1 minus C2. Right, and also in the previous case, if one had 2 minus signs here and plus sign here, it would have been still a positive feedback. So the conclusion of this 3 component system is that in the second case, when we have negative feedback, Hopf bifurcation is possible, and it's easy to find the condition for this Hopf bifurcation point is where the product A times B is equal to C.